Alright, so here's how our roller coaster works. So the funnel up here where you drop the ball in, and then from the funnel it spins a couple times and due to centripetal force it'll go towards the center. When it goes towards the center, there's this little beam right here, and this beam makes sure that all attempts at going into the hole are strictly the same. Now when it goes in the hole, then it comes down this diagonal in which it goes into this wide turn. Now in this wide turn there is a pad right here which makes sure any bouncing that happened won't actually cause the marble to jump tracks. There is some string over here that suspends the tracks in midair, and once the ball goes over here, it jumps down into the diverger. We were planning to make another track or a whole different branch, but we didn't actually decide to. So the marble causes this thing to go down, in which it safely jumps onto the other track, where it goes down this really steep turn, and this thing goes so fast that it actually clears the whole loop-de-loop, goes into another turn down here, in which then it goes down to the final loop-de-loop. And then over here is the stop mechanism where it hits this incline and then it kind of goes around.
This roller coaster is for those who seek a fast yet thrilling roller coaster and love the changing of directions and jumping of tracks.
Average speed was 3.02 over 4 meters per second, and this was calculated by the change in distance over the change in time. And our marble positively accelerates when it goes down the blue tracks, which are these here, and it negatively accelerates when it's going towards the top of the loop-de-loop. So for example here, as it goes up here, it's negatively accelerating. And it accelerates due to the change in direction while it's going in the funnel because it's constantly changing direction. And it accelerates due to a change in speed and direction when it's going down these wide turns because it changes direction and it's accelerating by going faster as well.
So the gravitational potential energy of the marble at the start is 0.032 joules with the height times mass times gravity formula. And then at the loop at the bottom here, the marble experiences the highest kinetic energy because it's at the bottom, the lowest point of the coaster, and all the potential energy has been converted into kinetic energy. And then due to the friction of the this flat track, the ball eventually stops and it goes around and then it loses all its energy and then stops.
A force is something that causes the object to change in speed. Alright. So as you may see, here's the diagram in which it's a balance force. So the balance force causes the object to not move and just be stable, but if you take one of them, I guess any of them, it will be an unbalanced force, which will cause the object to go or change its speed. So the first force is gravity, in which it always goes down, as you may know. So one of the examples of gravity is when all the tracks are being affected by it, in which they obviously go down. Normal force, so normal force is a force that is located, which is perpendicular to the surface, perpendicular, in which is a line that forms 90 degrees. So in the roller coaster, all the tracks, including the long funnel and the loop-de-loop, etc., all the tracks have normal force that is applied to it. Okay, so next force is friction force. Friction, in which is the force that counteracts the applied force, and it happens to every track, including the long funnel and others. So yeah. Okay, so the last force is centripetal force, in which the ball pulls towards the center. So it is located in the long funnel wall. So if you put a ball there, in which I now have it already. So okay, so once you put in the ball immediately goes to the center of the funnel.
So tension is defined as the pulling force of an object on one or two of its ends. So in this roller coaster, tension actually shows up, as you can see in the diagram, when the tracks are being suspended by string. So the tension holds the string up as when the track itself is pulling down, the tension on the ends of the string is keeping this track from falling. And then when the ball rolls down, then the tension's also there to make sure that it can accommodate for the gravitational force of the ball. So Newton's first law was an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless enacted by an unbalanced force. So now, a place where this may show up would be in your roller coaster at the end. So you can see at the end of the roller coaster, the ball comes to a stop. So since all the forces of the ball are the same, then there's no actual motion happening. So another evidence of Newton's first law would be throughout the whole roller coaster. So for everywhere, since the normal force is on a diagonal, so it's perpendicular to a diagonal beam, you see how the ball starts to accelerate, and that's because the motion keeps changing because the forces are imbalanced, and it's also part of Newton's first law because a ball which is in motion tends to stay in motion, but a ball which has an unbalanced force which enacts on it actually causes a change in motion. So Newton's second law is defined as the sum of the forces equal to the mass of the object times the acceleration. So this too is also applicable to roller coasters, and one example would be if you have a diagonal a diagonal track, such as the blue one, then you'll find that if you add a heavier marble, the amount of force that it's going at increases jointly. So if I had a lighter ball, you'd probably find that it's a lighter applied force, while if you have a heavier ball, it would be a way heavier force, because the sum of the force is equal to the mass times the acceleration, and mass is bigger. So if you have a lighter or heavier marble, it actually does not affect the acceleration, as acceleration is just changed in velocity over time. So acceleration itself is not relative to the mass of an object. So Newton's third law states that every action has an equal and opposite reaction. So in my roller coaster, at the end, I come to a stop, but that doesn't mean that Newton's third law is still in play. So if you look at the picture where the roller coaster ends, you can see how the ball is at the bottom, but then the normal force, which is pointing up from the surface, is actually a reaction force from the ball, which is pushing down on the floor. Another example of the Newton's third law is in a funnel. So in a funnel, there's a centripetal force which is keep bringing the ball towards the center, but at the same time there's a linear velocity which is keeping the ball out. So the way the linear velocity is actually countered is by centrifugal force. So with the centrifugal force and centripetal force, you get what you call uniform circular.